Okay, in this lesson, we're going to be dealing with radicals, and we're also going to be dealing with rational exponents, which means fraction exponents. So just to kind of show you where we're headed, we're going to be simplifying things that have radicals, sometimes with variables and fractions, and then we're eventually going to get to a point where we're dealing with exponents near the end of the lesson, and the exponents are going to be fraction. Sometimes they're going to be negative exponents, and we're going to learn how to simplify all of that. So I'm going to head back to the top, and I will be skipping a lot for this video. So anything that I did not do, you might be able to find on OneNote. First example will be really fast. What I want you to notice is the difference in A and B. In part A and part B, we're using the same numbers 9 and 16. But in part A, it's all under the same radical, and in part B, it's separate radicals. So this example is just meant to make sure that we understand that you would get different answers here, and it makes a difference whether it's together under a radical versus not. 9 plus 16 under a radical is 25, and that ends up being 5. Whereas in part B, square root of 9 plus square root of 16 gives me 7. 3 plus 4 is 7. And so what you want to avoid is trying to combine your 9 and 16 under one radical. So I made a little note, you can't combine it under one radical. Part C, I'm going to put a star on because that is on test or quiz. You would have a similar question. And what you should notice under this radical is you cannot simplify 9 over 16 because nothing goes into both. But one rule that we have for radicals is when you're multiplying and dividing, you can actually separate the pieces. So I can separate root 9 and root 16 just like that. It equals the exact same thing. And this works for multiplication and division. So since I did that, I now know what the square root of 9 is, what the square root of 16 is, and can simplify this to a nice fraction. And then the last problem is just meant to help us understand common denominators and how to add fractions together. So we've already dealt with the square root of 9 and the square root of 16. So I'm going to quickly write what this fraction would equal. Plus, it's 1/3 plus 1/4. But the common mistakes that I see would be to try to add 3 and 4 across the bottom, which you cannot do. You need a least common denominator. And that means that you need to figure out what is the lowest number that both 3 and 4 can go into as factors. And sometimes the fastest way would be to just multiply 3 times 4. The least common denominator in this case would be 12. So that's going to be our new denominator, which means I have to try to get a 12 on the bottom of each of these. So to get a 12 on the bottom of my first fraction, I would need to multiply the bottom by 4. But if you do that to the bottom, you need to do that to the top as well. Heading over to the other fraction, this time I would need to multiply the bottom by 3. And if you do it to the top, or to the bottom, you have to do it to the top as well. And so we are looking at multiplying across the top 4 over 12 plus 3 over 12. And last thing to be careful about is when you're adding fractions and you have a common denominator, it stays your denominator. Don't add them together. The denominator needs to stay put. If you have 4 out of 12 plus 3 out of 12, you have 7 out of 12. That's your final answer right there. In example 2, A and C, we have done these in the past multiple times, so I am not going to go through those. However, if you need help on these, just come in and ask me and I can go over it with you. The ones that we did in class, though, would be B, D, E, and F. And so I'm going to do B. And in B, we're supposed to simplify this expression that's being multiplied together. And my first thought usually is to try to break down the 6. And when you break down the 6, which you're going to find quickly will not really help you out at all, you don't have a pair. You can't do anything to break down the 6 that's going to help you simplify. So you might feel like, well, what do I do? I'm stuck. Well, remember in the past example, I said when you multiply or divide radicals, you can break them apart or put them together. I'm going to put this together. 6x times 3x under one big radical. You can only do this with multiplication and division, so just be careful about that. And the reason I want to do that is because once I combine my 6 and my 3 together into an 18, and my x and my other x into an x squared, I can find a pair in each of these things. So 18 is going to be 9 times 2, and 9 is going to be 3 times 3. And I do have a pair of 3s, and I have a leftover 2. With my x's, and by the way, in the intro to P3, we dealt with problems that involved x's under radicals. So look on OneNote if you need to see some examples of that, because that was part of the intro, which I did not make a video for. But for my x's, I like to list them out just like I list out other factors, and the same thing is true I'm looking for pairs. With x squared, you have 2 x's, so it's a pair. And remember, for every pair, 1 will come out. So I'm going to have a 3 come out because I have a pair of 3s, which I color-coded yellow. I'm going to have an x come out because I have a pair of x's. Notice there's no leftover x's at all. And the only thing left over is a 2. So my final answer is going to be 3x root 2. Put a box around that. And D is going to be super similar, so you can find that on OneNote, but I'm not going to do the same type of problem in this video. I will, however, head over to E, which is a little bit different because you are going to have more than just x squared. So let's do D really quick, or E really quick. And I'm going to do it the same way. I'm going to combine these into one radical. So I've got 2x squared times 6x. Combining this together, I've got 2 times 6 is 12. X squared times x to the first power. You can put a first power if you want to. You're going to get x to the third. And we break it down the same way as always. And you'll notice you have a pair of 2's, a leftover 3. And when you list out your x's, x, and x for x cubed. So there's 3 of them. You're going to see only one pair, but you have a leftover this time. So I've highlighted my pairs and I've underlined my leftovers, and for every pair, 1 comes out. So I have a 2 coming out front because I've got a pair of 2's. I have an x coming out front because I have a pair of x's, and be really careful, only 1 comes out, so don't put an exponent on that. Inside my radical is my leftovers, which would be a 3 and an x. Final answer, 2x root 3x. And for part F, you can check that on OneNote or ask me about it if you can't find it on OneNote, but it is the same type of problem. Heading to example 3, this time we have a fraction and it's got separate radicals, but remember I said if you multiply or divide, you can take them apart or put them together. Well, right now they're separated, so I'm going to try seeing if I can put it together, and here's why. If I were to put them all together under one radical, that's going to save me a little bit of work. Then I can simplify what's inside before trying to look for pairs. You could look for pairs from the beginning if you wanted to, but it's going to be more work. So instead, I would rather see if I can simplify. And I noticed that 48 over 6 can be simplified into, well, 48 divided by 6 is 8 over 1. And I'm not going to put the over 1 right now. So I know that 48 divided by 6 is 8. Then I have x cubed over x. And if you want, you could put a little first power there. If you were to cancel x's on top and bottom, your leftovers are going to be on top. And you're going to have x squared left on top. And nothing is left on bottom because 48 divided by 6 was 8, and I have no x's left on bottom. So this is now what I have to simplify, which is so much simpler. I break down my 8 into 4 and 2, and my 4 into 2 and 2, and I break down my x squared into x and x. And I've got a pair of 2's, a leftover 2, and a pair of x's. And then this is going to help me write my final answer, which is a 2 comes out, an x comes out, and a 2 stays in. There's no x's left over to stay in. So that's how I would do part A. Okay, I'm also going to do problem C because you're going to notice a negative exponent here. And I'm going to start it the same way where I combine it into one big radical. We've got 200 x cubed on top and 10 x to the negative first power on bottom. And I want to simplify what's inside to make it easier on myself. So the first thing I notice is that 200 over 10 can be simplified pretty nicely into just 20. 200 divided by 10 is 20. The other thing I notice is anytime I see an exponent that's negative, it tells me that I need to move the entire term. So there's actually going to be nothing left on the bottom, and on top we have x cubed, and then that x to the first power is going to move up there, making this 20 x to the fourth power. Breaking down my 20 into 4 and 5, 4 is 2 and 2, and then listing out my x's, and I'm listing out all 4 of them, I find that I have a pair of 2's and 2 pairs of x's. So I've got a pair of 2's, I've got 2 pairs of x's, and I have a leftover 5. So for every pair, 1 comes out, and that means that my final answer is going to have a 2 out front, an x out front, another x out front, and a 5 left over inside. For every pair, 1 x comes out. So I have x times x, which ends up being x squared, root 5, 2x squared root 5, final answer. And you will notice in these notes that the other 2 problems that I'm skipping match the ones that I just did. They're for you to practice, and if they're not on OneNote, then you can check your answers with me if you need to. But I'm going to head to example 4. In example 4, we're adding and subtracting things that are under radicals, which normally you can't really do a lot when you're adding and subtracting radicals. You can't add the numbers under the radicals with each other. However, if your radicals match, then you can think of it like a variable. Think of it as combining like terms. If I have 7 root 2's plus 5 root 2's, how many root 2's do I have? I've got 7 root 2's plus 5 root 2's gives me 7 plus 5, 12 root 2's. And the part that does not change is the root 2. You just add the coefficients out front. Heading to B, the only difference in B is that there is an x inside the radical, but the radicals still match. You still have a 5x inside each radical, and as long as they match, you're good to go. But the other thing I noticed is there is no number out front. So when there's no number out front, I'm going to put a 1. So I've got 1 root 5x minus 7 root 5x. And remember, we can just add or subtract the coefficients. 1 minus 7 is negative 6, and then the radical is root 5x. And remember, the radical stays the same. As long as you have like radicals, you can combine them. Heading to the next page, I'm going to skip a few of these that are similar to what I've already done, and I'm heading straight over to E, where you'll notice that you don't have like radicals this time. So your goal for E is to get like radicals. And you're going to do that by simplifying. 3 can't be simplified, but 12 can be simplified. 12 can be broken down, and when you break it down, you're going to find a pair. And so I'm going to rewrite this. I've got 7 root 3 plus, well, my pair is a pair of 2's, so a 2 will come out, a 3 will stay in. And you're going to notice in these problems that if you break it down correctly, your radicals should match. You end up with, adding my coefficients out front, 7 plus 2 is 9, root 3, final answer. I am going to leave the rest of these for you to practice with and check if you want to, either on OneNote or with me in person, and I'm heading to example 5. Heading to example 5, this is called rationalize the denominator, which really just means get the radical out of the denominator. We don't want radicals in a denominator. No radicals in denominators. They can be in numerators, not denominators. And there is a simple trick that's going to get a radical out of your denominator anytime you see it there. All you have to do is multiply the top and bottom of your fraction by the radical that you see in the denominator that you're trying to get rid of. It is we want gone. And in part 8, I am going to rewrite it to give myself a little more space. The radical that I want gone is radical 6. So I would multiply the top and bottom by radical 6. And that means multiplying across the top gives me 15 root 6. And multiplying across the bottom, root 6 times root 6, we learned in the intro to P3, which I do not have a video for, but it's on OneNote, that anytime you have a radical times itself, it's like you're squaring that radical, which means that a square and a radical cancel. You just get 6. And this will happen every single time. You're going to get whatever number's underneath when you multiply it by the exact same thing. Okay, so root 6 times root 6 is 6. And that's true for every radical times itself, which looks like, okay, we got the radical out of the denominator, we done. Well, you should definitely check and see, is there anything else you can simplify? Another thing we learned in the intro to P3 is that you can simplify numbers that are not under radicals with each other, but you cannot simplify numbers that are outside the radical with numbers inside the radical. So what I mean is 6 and 6 can't cancel because one of them's in a radical and one of them's not. The only things I can worry about simplifying are going to be 15 and 6. So ask yourself, is there a number that goes into both 15 and 6? And the answer is yes. 3 goes into 6 twice. 3 goes into 15 5 times. My final answer is going to be 5 root 6 over 2. There's no more simplifying I can do, and I don't have a radical in the denominator anymore. In part B and D, these problems are going to be very similar in the sense that you can simplify your final fraction, but I'm going to do B because there's a little bit more to it. So heading to B, I rewrite. And when I say there's a little bit more to B, I'm looking at the 8 under my radical, and I'm thinking there's a pair in there. So I can simplify more than what I did in A. So I'm going to start it the same way, though. I'm going to get the radical 8 out of the denominator by multiplying on top and bottom. I get 12 root 8 over 8. All right, so that is step 1. We no longer have a radical in the bottom anymore, which was the goal, but we can simplify 12 over 8 because 4 goes into both. 4 goes into 12 3 times, and 4 goes into 8 2 times. So I'm going to rewrite this again. I've got 3 root 8 over 2. And you think you're done, but we've spent all this time simplifying radicals for a reason, because when you have a radical you can simplify, you need to, because that's what a simplified expression is going to end up being. So this is not done yet. I'm going to simplify my radical and see what else I can do. Break down your 8, you're going to get 4 and 2, 2 and 2, and I'm doing this kind of quicker than normal because we've done this so many times. We've got a 3 on the outside still because there was already a 3. But when I broke down root 8, a 2 comes out for my pair of 2s, a 2 stays in for my leftover 2, and on the bottom I have another 2. So at this point, you are welcome to cancel your matching factor of 2. They're both outside the radical, they're both factors. You can do that, and your final answer is going to be 3 root 2. So A is going to be similar to C, and actually there won't be any final simplifying to do there. D is going to be similar to B in the sense that you will have to break down the radical of 12 at some point to keep simplifying. Heading to examples E through H, I'm not going to do all of them, but they do look a little bit different. So I am going to do one or two of them. I think I will start with F because they all look the same. They're going to be set up similarly, but F is going to have some simplification added to it. So first step is we know we don't want a radical in the denominator, and you will have to get the radical out of the denominator by multiplying top and bottom by that radical. So I multiply top and bottom by root 15. When I do that though, normally we're used to seeing one thing on top, one thing on bottom, but this time there's like two things on top with a plus sign in between. I'm going to put some parentheses, and I'm actually going to rewrite it as well. Parentheses on top only, and then root 15 on bottom, and we are multiplying by root 15 over root 15 because that is the rule when we want to get rid of a radical on the bottom. So on the bottom, it's going to be nice and simple because radicals will cancel when you square something. We just get 15. On the top, though, you have to distribute this, which is the reason I put parentheses. That root 15 needs to go to each term. So I'm going to make my fraction a little bit longer because it's going to take up some space. 15 times root 15. Well, the number not in a radical goes out front next to the radical. So 15 root 15, okay? And then we still have a plus sign. This is positive. And now we have root 10 times root 15. And I'll simplify that in a second. These things can get combined into one radical, which would be root 150. And so that's what I'm going to do. I'm going to say 15 root 15 plus root 150 all over 15. The hardest part of this problem is simplifying fractions. This will be the hardest part of the problem for every problem you see with fractions, okay? Simplifying can get tricky because a lot of times students try to cancel things they should not cancel. And right now, I'm not going to cancel anything. Don't cancel anything. But off to the side, let's simplify 150 under the radical. We get 15 times 10. We get 5 times 3 and 5 times 2. And we find that we have a pair of 5s and a leftover 3 and 2. So I've got a pair of 5s. My leftovers I put underlined. This equals 5 root 3 times 2 is 6. So I'm going to rewrite this. I've got 15 root 15 plus. All right, what did we simplify this to be? This we simplified off to the side to be 5 root 6. They're the same. Those circled things equal the same thing. All over 15. All right, last step, and it is the part where there are so many mistakes so often. How do we simplify this if we can? Notice, root 15 will not be able to be simplified at all. There's no pairs. That's just a 5 and a 3, no pairs. But when you have a problem like this and a big fraction like this, what you want to do is look at all of the outside radical numbers. I'm going to highlight all of them. The only way to simplify is if you can take a factor out of all of it. Not just two of them, all of them. So I highlighted all 3 pieces outside the radical, and I have to be able to cancel something from all 3 pieces. So taking a look at all 3 pieces, is there anything that can go into 15, 15, and 5? The answer is yes. A factor of 5 goes into each thing. 5 goes into 15 3 times. 5 goes into itself 1 time, and 5 goes into 15 3 times. My final answer is going to be 3 root 15 plus 1 root 6 can just be root 6. You do not have to write the 1. So that's the top. And on bottom, 3. And as much as you want to cancel 3's from everything, you cannot cancel 3's from anything in this fraction. And the reason is, even though I see a matching 3 on top and bottom, it needs to be part of every single term. And that means each term is separated by pluses and minus signs on top. So I would need a 3 in this term right here to be able to cancel that. So I cannot cancel the 3's right there because I need one right here to be able to do that. I needed it to be in all the pieces to do it, first of all. Second of all, I can't cancel anything from under the radical with anything not under a radical. So even though 15 and 6 seem like it could reduce with a 3, it can't because these are under a radical, so they don't count. So be very careful with that. I like to highlight every single piece that could potentially get reduced to see if it can. And in this case, I'm missing a factor of 3 in that piece right there. So don't do it. Don't try. I know you want to. Don't do it. The rest of the problems you can try on your own. You can check them with me. You can come in for help if you need help. But I am moving on to example 6. This time we are rationalizing a denominator, which means getting rid of radicals in a denominator. That's what it means to rationalize. But we have more pieces in our denominator. So normally you would want to multiply top and bottom by whatever radical it is you want to get rid of. But not in this example. You will not be able to just get rid of the radicals by multiplying by root 3 on top and bottom. And don't write this down. I'm going to erase it. Don't do it. But I'm going to show you what happens if you multiply by root 3 on top and bottom. Well, it's not going to help you. You're going to get 7 root 3 on top, which is okay. But on bottom, you get 5 root 3 plus root 3. And that is because I'm distributing 5 root 3 plus 3. And yeah, one of my radicals went away, but I just put another radical in there. So that did not help me at all. So we need a new trick. And we did this actually in the intro to P3. Off to the side, I'm going to show you what it is that I'd want to multiply on top and bottom. You don't need to write anything on your notes yet, just kind of pay attention. I had a 7 on top and a 5 plus root 3 on bottom. And I want to decide what is going to make my root 3 go away on the bottom. So I'm going to focus on the denominator only, 5 plus root 3. What can I multiply this by that is going to make root 3 go away? Well, I'm going to use some parentheses around it to multiply something else to it, and I'll do that in red. So what should I multiply that's going to make this go away? Well, I don't want to multiply it by the exact same thing, 5 plus root 3. I almost put a plus sign there. But if you were here for the intro to P3, or if you looked back at the notes for the intro to P3, we had a problem where we had the same terms and the opposite sign in between them, and we saw that it reduced really nicely to a whole number. So let me show you. I'm foiling this. I get 25 for my first term. 5 times 5 is 25. Then I get 5 times negative root 3, which is a negative 5 root 3. Okay, I have a plus sign here, which means that it's positive root 3 times 5, so this time it will be plus 5 root 3. I always put the number outside the radical in the front. And then lastly, I've got a positive times a negative, which is negative. Root 3 times root 3 is root 3 squared, which is 3. Remember, root 3 times root 3 is just 3. And we have to get the hang of that right there. So let's simplify what we have. I've got matching terms in the middle, opposite signs. Negative and a positive of the same thing cancel. This ends up being 25 minus 3, which is 22. I got a nice whole number, and the goal is to not have a radical and to have a nice number in the bottom with no radical on it. And I achieved it by keeping the same terms but changing the sign in between. And that's exactly what we're going to do in example A. We are going to multiply by the, and I'm going to use the term for it, conjugate. That's the name, which means same terms, different sign in between. So I want to keep my terms the same, but change the sign in between. So same terms, different sign in between. For part A, we already know that's going to be 5 minus root 3. We're changing the sign. On top and bottom, whatever you do to the bottom, you have to do to the top. So I have to do all that work to the top and to the bottom. And I'm going to rewrite that. I've got 7 times 5 minus root 3. I leave the parentheses there because I will have to distribute. And on the bottom, I'm going to put parentheses because I'm going to have to FOIL. 5 plus root 3 times 5 minus root 3. And again, these will have to get FOILed. Okay, so I multiplied the top and the bottom by the opposite sign in between whatever was on the bottom. And this will help me get rid of my radical. On top, I get 7 times 5 is 35, minus 7 times root 3 is 7 root 3, all over. And now we FOIL, which I actually already did off to the side in the video already, but I'm going to do it one more quick time. 5 times 5 is 25. 5 times negative root 3 is negative 5 root 3. So that's the two first pieces. Heading over to this part, I've got root 3 times 5 is positive 5 root 3. I put the 5 in front of the radical. And last piece, I've got 3 times negative root 3. Positive times a negative is negative. Root 3 times root 3 is 3. We cancel the middle, which will happen every single time, and we get 25 minus 3 is 22. 22 goes on the bottom. And I look and see, is there any factor that's in common in all three terms? It's got to be all of them. I don't see anything. So my final answer looks like that. Okay, the rest of the problems in this example are very similar. And you'll notice it gets more complicated for E and F because you have two radicals rather than just the one. But it's going to be the same process, and if you multiply by the conjugate on top and bottom, which means keep the terms but change the in-between sign, do a little FOILing, which will take some work, you will find your radicals will go away. So if you need help with anything in that example, you come to me, you look on OneNote, I can help you. But I'm heading in this video to example 7. Okay, in example 7, I'm going to do two quick problems. They're fast. The only thing you should notice that's a little bit different than normal when we simplify radicals is a tiny little number out in front of the radical. In all of these problems, you're going to see that little number. And what you should know is that when there is no number, that means you have a square root. And it's almost as if there's like an invisible 2, but we don't write the 2. So we look for pairs with a square root. When you have a different number, like for example 3, this would be a cube or third root. And we're not looking for pairs, we're looking for groups of 3 this time. So whatever number it is that you see on the radical, that tells you if you're looking for pairs, groups of 3, groups of 5, groups of 8, it doesn't matter, whatever number that is what you have to look for to be able to simplify. And square means 2, but remember, it's an invisible 2 that we usually don't write that tells us to find pairs. So if there is no number, you're looking for pairs, and if there is a number, you're looking for that number, but we break it down the same way. 24, I'm going to break it down to 12 and 2. 12 is 4 and 3, and 4 is 2 and 2. And I noticed that, yes, I have pairs, but I'm not looking for pairs, I'm looking for groups of 3. And so we want to find groups of 3. And I notice that I do have 3 2s. They don't need to be next to each other. And actually, I'm going to use a different color for them because I'm already using yellow somewhere else in this problem. So I've got a group of 3 2s. And then I have a leftover 3. So my final answer is going to be, well, for every group of 3, 1 comes out. So I'm going to bring out a 2 because I have a group of 3 right there. What stays inside the radical? A 3 left over that I underlined already, but be very careful. You need to write the cube or the little 3 on the radical. So don't forget this guy. This is part of your final answer. This is not a square root. This is a cubed root, and that is part of your final answer. So just make sure you remember to put that there. I'm not going to do B because it's super similar, but I will do C. And in part C, the only thing you have to do a little differently first is double check that these have the same number here before you try combining them. And since they do, you're welcome to combine them into one radical, 8 times 4 underneath it. You've got 4th root 32. Break it down, and this time we are looking for groups of 4. Okay, so I don't want pairs this time, I want groups of 4, so I'm breaking this down. And even though I see pairs, I have to keep going till I get groups of 4. And I've got a group of 4 2s. 1, 2, 3, 4. They don't have to be next to each other, but that's what I have right here. So final answer, for every 4, 1 comes out. So a 2 comes out. And then I have a 2 left over inside because this did not have enough to come out. And lastly, do not forget, this is not a square root. This is a 4th root, which has to be part of your final answer. The last one I'm going to do from this example is going to be a fraction. It's a little bit different. And just like in a previous problem, I will break it up into 2 separate radicals on top and bottom. They both get a 4th root. And off to the side, I am going to see if I can simplify each of them individually. So I'm writing them each out individually to see if I can get a group of 4. Remember, this 4 means I need a group of 4. So I'm breaking it down, 9 and 9, 3 and 3, and 3 and 3. There is nothing left over, and I have a group of 4 3s. So this equals just 3. That's it. There's nothing left inside the radical, so we don't put a radical. All right, let's do 16. 16 is 4 and 4. 4 is 2 and 2. Same with this 4. And I broke those down. So now I have a group of 4. Nothing left over. So there's nothing inside the radical, and I realize that 4th root 16 equals simply 2. And this is true because think about it. 3 to the 4th power in a calculator is 81, and 2 to the 4th power in a calculator is 16. So working backwards, it does check out. So just keep in mind that working backwards, it should make sense. But I can replace now my 4th root 81 and my 4th root 16 with what they equal. 4th root 81 equals 3, and 4th root 16 equals 2, and that is my final answer there. And the last example of this I have for you guys, and I know it's a very long set of notes, but this example has fraction exponents. And while I have you here, if you missed class and you're making up the notes, you can go ahead and put a little star on F, because that would be a test question. There may have been another test question I missed, but this definitely is on there, so keep that in mind. I'm going to do a couple of these and leave a few for you to do, but I'm going to definitely do A. I want you guys to understand how fraction exponents work, and I'm going to write a little example above. X to the 1/2 means the square root of x. And I know that the 1/2 part doesn't really show up here, but here's how it does show up. A square root has an invisible 2, and x is to the 1st power, which is also invisible. So the way that fraction exponents work is that x to whatever power goes in the numerator, and the radical, whatever we want the root to be, goes in the denominator. So here's another example. X to the 3/4 would be the same thing as saying we make our radical, and then we take a look at the example we have. Well, whatever is on top already of x stays on top, x to the 3rd. And whatever is on bottom tells me what my radical is, 4th root. So keep in mind that whatever is already on top of x stays on top of x, and the denominator is just meant to tell me what goes in the radical. But also remember that x to the 1/2 or anything to the 1/2 is just a square root with an invisible 2. Okay, so it's an invisible 2 if it's a square root or a denominator of 2. So we're going to head to A, and we notice that the denominator is 2. So this is a square root, and it's 64 to the 1st power. But the easier way to write that is you don't have to put the 2. It can be invisible on the radical, and 64. So square root of 64 is pretty easy to figure out. You could break it down, you could put on a calculator, you're going to find the answer is 8 because it ends up being a perfect square. So let's move on to something a little bit more difficult. I'm going to do F, and that's the last one that I'm going to do from this example and from these notes. The thing that I want to point out about F is you see a negative exponent, which does not mean a negative number. What this means is you need to move the entire thing that this exponent is on to a different side of the fraction. And you might think, okay, well, I don't see a fraction other than the exponent. Well, let's put this over a 1. And what we want to do is move to the other side of the fraction. Take this entire thing, it's going to go down here, and we're going to rewrite it. There's nothing left on top of the fraction, so I'm going to put a 1 because there's nothing there. But on the bottom, I've got 81 to the, this time we're going to put 3/4 positive for our exponent. As soon as we move it, it changes the sign. So now our goal is to figure out, well, what is 81 to the 3/4 so that we can replace it. And what that means is it's going to be a 4th root. So remember that denominator tells us 4th root, so we're looking for groups of 4. And underneath the radical is 81 cubed. Okay, so here's one way you can write it, But what I want you to think about is 81 to the third power is a pretty big number. So I'm going to show you another easier way you could write it. When you look at something that's a huge number and you feel like, what am I supposed to do with it? We still want to keep the fourth root on the outside, but I don't want to figure out what 81 times 81 times 81 is. So instead, I'm going to move that 3 out here to the front, which you are totally allowed to do. What you're allowed to do is you're allowed to figure out what it equals inside the parentheses and then do the third power at the very end. Okay, so I am trying to figure out what the fourth root of 81 is so that I can cube it at the end. And that is what's going to go here. So let's figure out, and by the way, I wrote that a little too big. It should be a tiny little 4 up there, which tells me that I'm looking for groups of 4. So I'm going to break this down. 9 and 9, 3 and 3 for each of the 9s. And I find that in my parentheses, I have a group of 4 right away. In my parentheses, there are 4 3s, and for every pair of 4, 1 comes out. And for every thing left over, it would normally stay in, but there's nothing left over. Don't forget, though, you have an exponent of 3 up top. So what is 3 to the third power? Well, that's 3 times 3 times 3, which is 27. That's not your final answer, though. That's what goes here. Final answer is 1 over 27. And I would practice something similar to this because I did have you put a star on it because it is a test question. And that is where I'm stopping with these notes. But remember, anything we skipped, you can look over on OneNote. You can come in for tutoring and ask. You can try it on your own. And as always, you definitely want to put something in the summary box because it has to be complete for you to get full credit on your notes. You can put anything you want that you think is a helpful tip that would be useful for you if you're flipping through your notes to see basic things to study for in a test.